Welcome to another GCBASIC video demonstration. Please like, subscribe, watch all the video, let the video run all the way through. No point in me doing this if you don't actually do those things, because YouTube won't do the metrics on me. Okay, great. Let's get into this. So this is all about compiler control, something called hash startup. I'll go through the what this is, and then you go, wow, this is cool. Okay, so let's just recap. GCBASIC is an open source compiler for AVR PIC LGTs. It supports 1,500 microcontrollers, and it's cross-platform with common code translation, which means you can take the code from a PIC, AVR, or a LGT and take it to another chip. It just sort of works. Anyway, so seeing this diagram, if you've been watching the videos quite a lot, and what happens is in GCBASIC, I'll just show you the basics. If you take a source program and we compile that source program based upon a set of constraints from the chip itself, and we take it into a preprocessor, but alongside that we bring in some libraries and a DAT file which describes the chip, and we take it through code translator. Oh, that should come together. And we generate some code, go through an assembler, and we create at the end a hex file. And it sort of works. Now the important thing here is that we've got a source program, tick, that's yours, and they've got libraries, which are standard libraries, which have been developed over many, many years, which sort of generally work. And however, sometimes they don't, and you need to control the compiler to help you make that solution. So if we look at the concept of operations of how this all works, we go back to specifically the source file and the libraries. There is a concept of operations that says that when these files run, they're full of libraries, and those libraries contain all the knowledge that's been generated over the last few years. One moment, take a little cough. And to make sure they run properly, each source file or library may have a command in there called hash startup, and that will always execute, and that will initialize that device, like an LCD or your program with a PPS, for instance. And those controls have always been there, and the one that's always called is INITSYS. When you start your program, you write your program, tick here. Down in the preprocessor, it always adds in a call to INITSYS, which sets up the clock and all the ports for you. That's the automation piece. You have no control over that, or had no control over that until the latest change. And I'm going to walk you through that change. So, concept of operations, you have a hash startup directive. It's always been there, and it allows you to execute code just after the system is initialized, as the system initializes. So you can say, set up the initializer system, set up this the PPS, which is for the more modern chips, set up the serial, set up the LCD, and they've all done that because they have this thing called hash startup, and it says go call this subroutine. And so it defines that subroutine that's executed during the startup phase. It's configured for you, and really you don't have to do very much. The only one you might actually see is PPS in it. If you're using a PPS chip, you need to do that quite early in the process, and we sort of even give you a sample for that. And it makes it very, very streamlined code, efficient, highly readable, because you know where to look. So in terms of what this looks like, the source code, your source code and libraries contain many, many subroutines and functions, but each source file can only have one sub. Your source program can have one sub, startup sub, and that has a name, like a subroutine name, and a priority. And that priority sets it in a list, and you can then prioritize where they sit. Normally, INITSYS is the highest priority, and then if you want it to have PPS, you put an 85 behind it, and they go up to 100. And you can sort of prioritize where they come. And that helps support the priority of initialization. So if we look at one in particular, source code and LCD.h, and it'll be very apparent to you in a moment why this is important, is you normally call PPS in it with an 85, and it will go and call a routine called PPS in it, and it will set it up. If you have the LCD, it will automatically call something called INITLCD, and it will then set up the LCD for you. Now, that's because those two have startup commands, and many others have startup commands. Many others. And this is where I got caught out the other day, and that's why I'm doing this video. So I bought something off of eBay, and it looks like this. It's a bit of kit. I'll push the reset button for you. This was £6 English. This is an absolute steal for it. Look at this for prototype board. You've got an LCD. This is the actual firmware that was installed. You've got potentiometer, different chips, clock source, sound, EEPROM, reset buttons. Just so much stuff for £6 English. And anyone who sees these on eBay should just go buy them because they're extremely good. Look, prototype area. Oh, just absolutely terrific. Let me have a look what we do here. We've got a voltmeter up, and I can put my voltmeter in it. From a learning standpoint, pretty cool. Okay, and what I was going to do is I was just going to very quickly just emulate this in GCBASIC and then sell this, and that's what I will do. But it didn't work. Let me explain. So I have a new LCD. That LCD failed to initialize. So I wanted to figure out what's going on. But it may be in the future you have your own LCD routines you want to write, and you don't really want to overwrite what's in the main libraries because they are managed libraries. So how do you manage to stop the existing library from doing what it's doing? And I could not stop it. And if you want to write your own initialization routines, you cannot stop that either, because that was the way the compiler was built. But I've changed that in the last build. So let me just take you through what I was looking at. So I have this LCD, just saw it on the screen, and it has some connections. I looked at the schematic because the documentation is still available. It's only a few years old for £6. Well, snip, okay. And I go, okay, I've got some ports here. I've got some ports here. But these are the data ports. These are control ports. And I've got an LED controlled it down here. It doesn't really matter what it is because I quickly knocked up a program. And I'll just take that out because I'll just zoom in. Here's the chip as per the option explicit. For those who haven't seen it, just need to define the variables. And I said I need an LCD IO4, which is what this is, because it has 4 ports allocated to it, and it's got an RS line, RW, enable, and a power line. And I press function key F5, and it will then go away. It will compile it, and this is the test program, a standard test program, so we know the test program works. Look in this mode here. It flashes the screen. It's flashed it, has it? Yeah, it's gone black. Nothing. No display. And this puzzled me because I'm thinking, oh, that looks just like an LCD, and it's putting random data on it. It's sort of the chip's operating, and I couldn't figure it out. So I thought, I'll tell you what I'll do is I'll quickly change the LCD initialization routine, and then I'm thinking, hold on a minute, I'm just going to destroy all the value of all the LCDs that work. Why would I want to do that? So what you can now do is you can control the LCDs, this startup command, which you couldn't do previously. And I'll show you how that's done. So in my program, I'm just going to put in a little, it's just a constant, not ocular OM 1614, and that's actually on that display. And if I show you, this resolves it, but it's what's going on in the background that's important. And we'll cut to that in a moment. Now it works. Okay, it's now doing the test exactly as it should. So I mean, I know it works because it was going to work. So what has changed? It's this control that you've now got. Let me take you through that control. The compiler now supports the updating of these startups with your own routines. You can even cancel the startups, so you could write your own. So the compiler will search for all the startups and update all the sources across all the libraries as you see fit, just as in this example I'll show you. So to do that, you would say hash define INITLCD, which is the second, this one here, and you'd say, right, I want to have my INITLCD, and it won't change the library. You just have to create a subroutine called myInitLCD in your program, and it will just take the startup command and replace it. If you want to cancel it completely, you just don't give it a second parameter. And there's no second parameter. The same for INITSYS. And we'll look at some assembly. So if you wanted to have my own INITSYS, you would literally say INITSYS and then give it another subroutine. If you wanted to cancel it, you just say that. Let's try that. Let's just try this and see what happens. So we know this program works. We can see it working here. I'll go to Zen mode so you can see it. If I come into here and I go hash define INITSYS, no parameter, it will cancel it. How do we know it's going to cancel it? Well, we can look in the assembler. We can see in here, look, in the assembler, that we've got a call to INITSYS and something called INITLCD OM61614 LCD. Oh, what's going on here? That's because I've changed the behavior of the compiler. Watch this. So all I've done is created a constant that's got the same name as the call, and that call has been vaporized. There's no reference to it in this assembler. So this now will not initialize this chip correctly. Let me just look. Check. This is all LCD stuff. There is no INITSYS. I can just do a search on that. Look. INITSYS has vaporized. I was just on the search, didn't find it. Well, if I wanted to say, right, my INITSYS, compile that. So down the bottom, INITSYS has not been defined. Inspect the ASM. That's because you don't have a subroutine called myInitLCD. You can control this now down to that degree. Let me show you how I got this ocular working, this ocular display. If I take out that constant and we look at the program in assembler, it's the easiest way to see this. It says INITSYS, INITLCD, and INITLCD is the old INITLCD. And guess what? If I reset this thing, I didn't reprogram it, so it doesn't matter. It doesn't initialize it properly. If I had programmed it, it would not have programmed it. So let me just program that. So what I need to do is get that redirected to another routine. And I've added my new routine into the knowledge base. So watch this. Define this ocular. What have I done with that? Well, over in my bit of code here, I've said this. Really quite clever. This is really very clever what you can do. Let me just zoom in for you. I thought I was going to zoom in. I just can't. Oh, there you go. If that constant exists, then I have said, rather than call INITSYS, assign that constant with that subroutine. So this is a subroutine change. This changes the INITLCD to a specific initialization routine. It requires a build greater than 1449, but it will call something that's called INITLCD OM1614_LCD. If I do a find on that for us, I am doing a find on it. There is a routine that's down here that's got my own routine up. The rest of the libraries hasn't changed. All I've done is change the initialization. Clever. So now you can write all your own routines in here and you can redirect any startup routine. You could not do that previously, not possible. So in here I've got this, I know I've got this. I know that when I compile this, I've compiled it, I'll look at the assembler and we will see it change in here. It's changed it in here. did not change the library. All I've done is put some logic in there to say redirect it, and you can do it any way you like. Let me think of a way of showing you. If I wanted to call something in another library, you would simply put a hash define its startup name and then the routine that you want it to go to, as in the slide here, as in this explanation. We might take all those comments off. So if you wanted to call your own INITSYS, you just define it like that. If you wanted to cancel it completely, you can do that nowadays. So if we come back into some source, let's just open up first sample. All I'm going to, oh, here's first sample. You can see I've been playing with it. Oh, that would do actually. That's a good example. No, let's just do that. Compile that. What we're going to do is look at the generated assembler. It says in here, well, the first thing is where's the vector? Here, this is the first vector. Jump to this program, jump to this point, and that is the end of the program. Because look, it goes straight to baz end, which puts it to sleep. You've essentially got a skeleton compiler. It sets up the config automatically, obviously. Yeah, you could even overwrite all that. So it's very, very clever. So I turned off in my source there, if I can show you. First sample, I said, INITSYS, don't just cancel it by having no definition. So if I erase that, function key F6, we'll look at the assembler. We can now see it's put the callback in here, and it's got all the code that goes with it. And you can do that for any routine now in the latest build. It's fantastic control. So done the lab. So summary. New compiler controls give you absolutely unbelievable flexibility to improve and ease your development of solutions. You can you can leave the libraries as they are. You can now then write your own routines and redirect as you see fit. As I said, this is after build 1449. Enjoy greater compiler control with GCBASIC.